say that as you change the voltage of the body, you will see that the VT would change. And as VT changes, you will also observe that leakage would change. Okay. So when we apply any body bias, there is an expected impact on leakage. Body bias, or even when we do not apply body bias, the very fact that my source and drain, now let us talk of it in terms of the stack of an NMOS, of a NAND gate. Now that this particular device, look at this, its body terminal is at ground. But what is the value of the source terminal? If this device is off, what is the value on the source?
Some finite value above ground.
The value on the source could be VDD also. If my if A is on, if A is 1 and B is 0, then what happens? This starts to charge this node. So this internal node could be VDD also. But if A is also off, A is also 0, then this internal node could be anything. Need not necessarily be VDD, but it could be some floating number. Are you able to see this?
So when A is when it will be VDD, but otherwise we cannot clearly say what it will be.
Yeah, some value Vx would be there. What that Vx will be, we can again apply Kirchhoff's current law and voltage law on the on the stack of NMOSes, considering their off resistances, everything. We can find that value of Vx, but so we can find that out. But we say that it is not VDD, it is somewhere intermediate. Exact value we do not know. So what happens? There is a voltage between source and body that is effectively getting applied. And that is what we call as body effect. It leads to increasing leads to increasing in VT and therefore reduction in leakage. It is also called as stack effect. Okay. So what does this mean? What does this entail for us? Yeah, this is again got stuck.
Sir, could you please say what is stack effect again, sir? I got disconnected, sir. Sorry.
Okay. So when one of the inputs is off, let us say B input is off. Yes, when the B input is off, A input is on, we know that the voltage at the intermediate node is VDD.
Yes, sir.
When A is also off, that is A is also 0, then there will be some value at this particular node, intermediate node.
Yes, sir. Yeah.
Whatever it is, one thing is clear, that there is a supply or there is a VSB that this device will experience, because body is definitely at 0.
Yes, sir.
And we are saying there's some voltage at the source.
Yes, sir.
So we will have a change in VT of the device. The VT of the device would increase. And what do we observe? We observe a reduction in leakage. This reduction in leakage is called as stack effect.
Sir, how did the leakage reduce, sir?
If VT increases, what happens?
Okay, sir. Forgot. Yes, sir. Thank you, sir.
Okay. So that being said, what else do we say? We say that what we do observe is that in a NAND gate, then as you change your inputs, see, the stack effect will happen differently when the inputs are 1, 0 versus when they are 0, 0. Are you able to see this?
Yes, sir.
So with that body effect happening differently, over there, we would actually observe that the leakage through a stack of 2 or 3 devices can actually reduce by orders of magnitude. For example, if all the inputs in the NMOS stack are 0, then the subthreshold leakage is 0.4. But when all of them are 1, then essentially, let us not say all of them are 1, let us say 110, then the subthreshold leakage through the NMOS side is 5.6. When all of them are 1, then the PMOSs are leaking. Then the entirely different leakage mechanism has come into picture. But until here, we are looking at the effect of body terminal only, like the body effect only. Over here, there is no body effect. But over here, there is a full body effect coming into picture, both on Vx and on Vz.
So why would there be leakage when A and B are 1 and C is 0? Because the intermediate node will be connected to ground and so will the body.
Yeah, but leakage will happen from Y to Vz, na?
Yes, sir. So, but SB is 0, so VT will be...
Yeah,
Okay, yeah.
so in
Okay,
that
okay,
case, there is no
okay.
stack effect. See, did we
Okay.
take any stack effect there?
Yes, sir. Yes, sir. There is
That is what we are saying.
Okay, sir.
That is exactly what we are saying, that if, so depending on which terminals are 0, which ones are 1, we will have stack effect or not, no stack effect.
Okay, sir.
Hai na? That is exactly what we are saying.
Yes, sir.
So this is what you are also observing in your simulations. Am I right?
So when it is 100, then there is no stack effect it is showing. Okay, no.
There's a stack effect on VZ.
Okay.
Hai na?
Sir,
Yeah. Yes. Yeah.
Yes.
sir, how are we supposed to look into this specific term? I'm like, I substrate or I gate or I total. How am I supposed to look into that leakage current, sir? Exactly.
Components of leakage, you can measure the current at the gate terminal. It will give you the gate leakage. You can measure the current at the drain terminal. It will give you the drain leakage, subthreshold leakage.
Okay, okay, sir. Okay, thank you. Sir.
Hai na? You just probe and measure.
Yes, sir. Yes. Thank you.
And do you see why gate leakage is changing so significantly? When is gate leakage happening?
All inputs are high, sir.
So gate leakage is happening in all those situations where the gate input is high and these inputs are 0. So when all these are 1, A, B, C, all are 1, then it is 0 at all the places. So there is highest gate leakage. When all inputs are 0, there is no gate leakage. Huh?
Sir, what is the second column actually? So what is written in the what is the heading, sir? Can you just, it is blurry.
This is I sub, this is
Okay.
I gate. Okay.
So sir, like we basically see the stack effect for every different node, and wherever we will see that the VSB is kind of greater than 0, that will basically for that particular device that subthreshold will reduce.
Yeah.
Okay. Okay.
Okay. So this is, so you will not really do it for every gate and everything, but yes, to do an analysis, you should be able to do it, for example, for a simple NOR gate also. How do you expect the leakage of a NOR gate to change in different cases? Okay. So depending on your input combination, the gate leakage would change.
So, but how do I say that? How do I conclude? I mean, what reason I will give for change in gate leakage?
वही तो बताया ना, if there is a voltage at gate and there is a voltage on the source or drain, due to which, let us say, just give me a minute. So there is this so what is happening? इसको भी अलग कर देते हैं. Just give me a minute. So what we are saying that if the voltage over here is very different from the voltage over here, then there will be direct leakage from gate to drain and source, let us say. Okay. So what happens? The voltage on the source and drain is also reflected across the channel region, the transistor region, and tunneling would happen. Let us say this is 1.2 volts and this is 0. So the channel region is also all at 0. So 1.2 volts across a very thin gate oxide. Let us say 0.1 to 1.2 nanometers or 12 angstroms. 12 angstrom device, 1.2 volts across it, there is bound to be gate leakage.
Okay, sir.
So tunneling happens. Tunneling means electrons from one side of the dielectric. So what is this? Let us say this is the gate dielectric. This is and these are your source and drain region. This is gate and this is your source / drain region. So what happens? The electrons simply tunnel. Despite there being a barrier, they don't really climb the barrier. They simply tunnel by the Heisenberg's uncertainty principle. And you have some current flowing. Okay. And that is why gate leakage would change when you apply depending on inputs.
Sir,
Okay.
is it only with drain and source, or is it also with bodies tunneling?
Body also. Body also.
Okay.
But that
Okay.
will rush into those electrons that will enter into the body will rush into the source and drain region. So it will be visible as source and drain thing only. Faisal?
So I am not able to get the stack when the stack effect is getting 0. Like,
Okay.
yeah.
So in this particular thing, let us say, so let us look at it over here. What are we saying? We are saying that when inputs are 1 0 0, let us say fifth row. So A is 1.
Yes, sir.
A is 1 means Vx is equal to 0.
Yes, sir.
Now what happens to Vz?
Vz can't be 0 because
Vz can't be
somewhere
0.
connected.
So there will be some stack effect.
Yes, sir. Okay.
Now let us look at the 101 case.
0.
C is 1 and A is 1.
C is 1 and
Since C is 1, across the NMOS, VDD will get transmitted to Vz. It becomes VDD minus VT.
Yes, sir. Yes, sir.
And since A is 1, therefore Vx is equal to 0. We're not talking about stack effect anywhere.
Okay. Okay.
Because there is a deterministic voltage. We know what it is.
Yes, sir. Yes, sir. Stack effect mein we don't know the voltage.
We can find out, but abhi ke liye we are simply saying there's a stack effect.
Okay. Okay, sir.
So, but then why you have written the 0 over there? I mean, it should stack effect is there. Right? Okay, VZ is there. Okay, fine.
I'm sorry. I did not get your question, Raghav.
Yes, sir. So, I mean, in the case of 0 1 1, we okay, we are getting VDD minus VT. Okay, right. So there is no stack effect, right?
Okay.
Okay. Yeah. Yes.
Yeah. So
what does this intermediate mean? I mean, what does intermediate A is reflecting? This.
You tell me, and just analyze it yourself and tell me. We are saying A is 0, B is 1, C is 0. So VDD minus VT cannot come to either
VZ.
Vx or Vz.
Yes, but VX
There
and
is
VZ
some
are
voltage.
same.
There's
Yes,
some
sir.
voltage which would appear at both Vx and Vz, which is also again different from the stack effect as we are talking about it. It could be similar, but because there is some on resistance of N2 which also comes into picture now, you cannot really say that stack effect पर ही voltage आ जाएगी.
Okay, I mean it is not
We're
neither
not only
stack.
talking about off resistances over here now. There is a non resistance also that has come into picture.
Okay, so it is neither stack and neither VDD minus VT. So it's
Yeah.
okay. Okay.
Sir,
Okay.
and these gate leakage currents, this 6.3, 12.6, and 18.9, they are exact, I mean, multiples of 6.3. So does this mean that we can, depending on the state, I mean, depending on the type of input, we can determine some nodes, count some nodes that that are on or have some voltage, and then we can determine the exact multiplication factor
Yeah.
for the.
That was what we were look also in a way looking at now. If this many gates are one and there is VDD, like look at case 011. What is happening there? In the case of 011, my Vx and Vz are both as VDD minus VT. Even for the devices where the gate is at 1, the differential across the gate is just VT. So there is no tunneling that will happen. But when the differential across the gate is full VDD, that is when tunneling happens. So as soon as you put, for example, Vx equal to 0, you see currents are in the range of 6.3 nanoamperes.
Okay, sir.
As it became 0 for both Vx and Vz, current increased further.
Yes, sir.
And then in the last one, it's the PMOS leakage current that is coming into picture.
Okay, sir.
Okay. So I will have to reset it once again. Just give me a moment.
Sir,
Yes.
sir, I don't know if this is a basic question or something, but sir, the NMOS which is present in the center, sir, I'm between two PMOSes and one NMOS. For suppose we are considering a NAND game. So in that, sir, could you please explain why we are connecting our body to ground, sir?
Why we are connecting our body to ground? You tell
Why
me.
not to source directly?
You tell me. What is the physical structure of the device?
Physical structure. Yes, sir. For
If you
NMOS,
have to connect the body to source somewhere, let us say Vx somewhere, and to ground elsewhere, what do you need? Can you have the same P-well in which the two devices can be made?
people.
Finally you're making these devices in P-wells, no? NMOSes
Yes,
in
sir.
P-wells.
Yes, sir. Yes,
So
sir.
can you make them in the same P-well? If you have to keep different substrate voltages, can the P-well be same?
So,
Or let us put it differently. If the P-well is same, can there be different voltages on the body?
no, there can't be, sir. Yeah.
Then why are you asking this question?
Sir, but okay.
Okay.
So we
So
just want to
we
maintain a
have,
voltage.
why did we cover the layout part before this part? So that you understand that something is not possible in terms of a layout. Hypothetically, in a simulation, you can put whatever value on your body.
Hmm.
But then if you have to design the layout of that and you design it the way we do, then the body terminals will all be actually shorted, is it not?
Yes,
You
sir.
do not
Okay.
have different bodies in which we will lay out those